Hello everybody, I'm Wojtek Burkot. I'm working for Allegro technology organization, but as you could guess from my talk, I had a history behind me. So in my previous life, or several lives back, I used to be a physicist, doing high energy physics at places like CERN and others. And the love for physics remained within me since those days. So regardless of my current job, I usually keep working on quantum computers. What does it have to do with the theme of this conference? I hope I'll get to in several of the last slides. All right, so I'll be talking to you about where we are and whether we could actually foresee a singularity ahead of us, a breakthrough. And I do believe that we are lucky enough to live in such a time that this actually is possible. How many of you have heard about Moore's law? Wow. How many of you have actually technical background, STEM or computing? Please raise your hands. All right, I'm trying to tune the way I'm speaking, and yes, obviously no physicists around, so I'd rather not go into solving Schrödinger equation for the quantum computer. As we are progressing with the technology, getting faster and faster, and actually synchronizing computations done in different areas of our computational media becomes more and more important. If you think about cloud computing, distributed lock mechanism, enabling parallel computing is something which we are after. You are mostly too young to appreciate that actually several decades back, synchronizing individual bits of the register was exactly that kind of task. For the first real computers, which actually were not universal computers, but rather flight simulators done for US military. Fast forward to today, and we are running cloud machines, and since you said that you know what Moore's law is, I'll go to the next slide. And growth is good, essentially. That's why you'll see mostly straight lines going up towards the upper right corner of the graph. What those graphs mean? Actually, I made them small enough so you can't read them. Essentially, they mean that the growth is good, so going up that way is okay-ish. But frankly, what that means is that the area occupied by a single transistor decreases. As we progress, it decreases exponentially. In a sense, well, you can see the exponential growth here just because the scale is log. That's why you see the straight line. If you notice, there is one graph which goes the opposite way, the one in the red frame. And that's actually the original version of the Moore's law. I guess what you know about Moore's law is related to phenomenological observation, which I just mentioned. That there's more and more transistors to a wafer, to a die on silicon. How it all started? Actually, the graph going down made perfect sense. As this, I don't know if you came across this graph ever before, is the original plot of Moore's law. Moore actually was one of the founders of Intel, and the graph was all about growth and growth of economy, which is actually plotted here. If you think what's on the axis here is the number of components per wafer, going that way. And then the number of transistors. If you think about how the production process goes, you could expect errors. So essentially, it's good to make the integrated chips as large as possible, having as many transistors as possible, except that then a single error in the lattice of silicon will spoil the whole chip, meaning there is optimum somewhere. And those optima, as the time progressed, are moving down, right? You see the first curve, this almost parabol there, is marked 1962, then 65, then 70. And that's the original version of Moore's law. This was only about the economies of scale, only in the transistors and the large scale of integration of chips built of transistors built on silicon, nothing more. And then people come across that idea that if they extrapolate this curve towards early computers built on relays, and to today's technology, when the silicon is a thing of the past for the fastest of the machines, this can be actually extrapolated. And that's the only graph going downwards on the previous slide. And we can look into detail of that one here in the magnification. We are somewhere here, right? And actually, if you look at the right-hand scale, this is the process, meaning ability to photographically embed transistors or structures into silicon wafer. This is about the size which can be actually constructed on the silicon. And it all looks nice, especially that it is curving downwards, meaning this miniaturization is accelerating. But sometime around 2020, which is the right-hand side end of this scale here on this graph, we'll be very close to getting into, well, the graph says about 10, but as you can see, the curve actually touches the line before that, meaning we'll be sometime in 2033 when the size of the structure, if the graph continues, the size of the structure will be about the size of the atom, which is like 0.5, 0.1, 0.5 of the nanometer. What does it mean? Essentially, you think that at that moment in time, we'll be able to embed a single bit of information onto a single atom. Sounds amazing, right? Except that at those scales, you can't avoid quantum effects. Well, you well know that most of today's transistors operate in the quantum regime anyway. This is the effect which doesn't exist classically. And we sort of can average over the tunneling effects in the transistors and use this as the viable technology. Very low error rate, very large scales of integration. It's completely different when we go down to the single atom. And this is not just a possible technology, but that's where we are heading. So what will happen in the scales of below 1 nanometer? It's more like 1/10 of that, but still, about that time. I do believe that changing into the quantum regime of the calculation, which by the way was postulated a long time ago. I guess it was back in 70s by some obscure Russian papers. Then Feynman got notice and produced a paper about harnessing the power of quantum mechanics for computation, as opposed to the classical computers, which essentially are modeled by the Turing machine, which in turn reflects the classical physics. Anything which can be computed essentially is about physics. Namely, our word, for any simulation we run in it, performs. So it is a calculation, how to abstract, how to embed that into silicon, how to get idealizations which simplify things, is a matter of the computer science in general. but underlying there is physics. Always there is physics. So is getting into the quantum physics regime significantly better paradigm for computation than the classical one? And that question stood open till, I guess, 1994, where Peter Shor came up with the algorithm building on the work of Simon and others before him. But for the first time, he showed how to factor large numbers. Well, how to factor numbers would be the more appropriate wording. How to factor numbers using quantum computing. And he could actually calculate how it would scale. So if everything would scale as he imagined, if you can get more and more entangled qubits, you will be able to factor faster than on any classical machine. And this is like theoretical limit. Maybe some of you one day will find a classical algorithm for factoring. The best known algorithms are slightly sub-exponential. It's like 2 to the power of log of n to 2/3, meaning slightly sub-exponential. Essentially meaning that finding larger primes is difficult. And if you think that I'm already lost any contact with the reality, that's something you use every day. All the banking protocols use RSA and public key cryptography, which is essentially based on difficulty of factoring large primes. Shor's algorithm can factor numbers. Well, look how it progressed. In 2001, Shor was able to demonstrate on something which is almost a quantum computer built by IBM that he could factor 15, 3 times 5. Great achievement for the first time ever. And then it progressed. Almost nothing happened till 2012, where 21 was factored, but the very same year, people were able to factor 143. Great achievement, right? Just 2 years later, 56,153 was factored using quantum computer, actually slightly different one, namely not following the Turing principle. It was annealer, much like the current D-Wave hardware, slightly different. So it looks like the progress is there. We are getting exponential speedups, but putting things into proportion, think about currently known largest prime used for, can be used for RSA, like encoding and cryptography. And those numbers have 17,425,000 digits. So getting from factoring something like 56,000 to a number which is millions of digits long is really quite a long way. So that's where we stand today, but the progress being made is tremendous. If you hear people talking about quantum computing, they'll tell you that the huge power comes from the fact that you can actually have a superposition of 0 and 1 in a single qubit. I would say it's not that important. It's not that important just because the quantum mechanics is extremely linear, in a sense that the best experiments conducted in real world confirming linearity are those in quantum regime. This is so-called G-2 experiment, 12 digits of linearity proven, right? So getting a superposition of 0 and 1 in single qubit, no biggie. The real thing and the real power of quantum computing is from the entanglement. Namely, several of those qubits, if operated on them simultaneously, can behave as the number stored over those qubits performs as unit. And again, from that on, you get a superposition. You can have multiple of those together in the register. But without entanglement, there is no real quantum computing. Besides Shor's algorithm for factoring large primes, or for factoring large numbers into primes, there is something else which was actually the foundation of going that way, namely trying to simulate quantum mechanics on classical computer is inefficient. And frankly, if you prove that you can simulate quantum system efficiently on the classical computer, it collapses the complexity hierarchy, which is a pretty cool result in itself. Some of the original authors claimed that actually quantum computers can solve NP-hard problems in polynomial time, and they keep saying that, or some of them keep saying that. Well, nobody have proven that. And actually, if you know what Groover's search is, there was a really clever algorithm showing that you can really speed up search in the unstructured database. If you think about any probabilistic argument, you'll have something of the order of n attempts to find a marked item in the unstructured database. Very clever algorithm by Grover does it in the time which is proportional to the square root of n. Significant improvement. And that's the reason of actually doing quantum computing at all. By the way, this result was proven optimal even before it was found. So the first paper proving optimality of the square root of n happened before Grover's algorithm. What are the obstacles? Mostly, essentially, to behave as for the register to behave, to hold multiple numbers long as the register is long, it takes isolating the system from the external world, and isolating to the point which is unimaginable in anything else. It's like Earth magnetic field is several orders of magnitude too high for that system to be stable. So you'll see the effect of the Earth magnetic field even behind shielding, and so on and so forth. And any operation of that system or any data input actually requires getting through that barrier. So on one hand, you want the system isolated. On the other hand, to perform any computation and get the results out to the classical world, you need to break that barrier. Not easy. And those bloody systems do not, as you can see in the real life, right? Essentially, if I do this, there is a chance that my food will actually tunnel through the chair. Doesn't happen in our world, right? So the quantum effects average out at the scales we operate in, just because the momentum is not the right size, the position precision, measurement of the position is not the right scale. So we do not observe those effects. So it requires a really clever experimental setups to battle both decoherence and the scaling problem of the quantum computer. Yet another problem is that most of our current algorithms would not work. You can't copy reliably quantum data. So essentially what it does, I'll get to that later. What it does, it prevents any kind of backtracking. You can't make a copy, perform the calculation, measure. If you don't like the outcome of the measurement, use the copy to create another copy and measure again. It doesn't work in the quantum regime. But despite that, those things started getting real. You might have heard about D-Wave, the Canadian company which does commercial quantum computer. Well, I'll challenge that notion. I would say this is celebrity computers. They sell them though to people like Google and others. So Google works with D-Wave, doing the optimization of their classifiers for Google Glass, which they abandoned, and for image recognition using quantum computer. It can be done on the classical machines as well, at least the way they do this. The other large organization having successes recently is University of Santa Barbara, University of California in Santa Barbara. Fantastic group, and they found something important. They created 9-qubit worth of hardware which performs computations of 5 of those qubits. The remaining ones are used for the error correction. A lot of work has happened in IBM on the algorithmic side to preserve coherence and make those things available. A lot of work happened in MIT. Actually, those guys built the diamond-based quantum memory, which holds the superposition for minutes. Well, it's not exactly cheap, being based on diamonds, but still. This down there means that there is yet another organization who is extremely interested in doing quantum computing, and for the security reasons, I wrote it white on white, so you can see it. And if you quote me, I'll deny I ever said this, NSA. And you could have seen that in the WikiLeaks, fall to the trap of efficient quantum computing with their project named Penetrating Hard Objects, I guess, or Hard Shields, sorry. So they're interested too, and they wanted to break the encrypted communication of everybody else. So, as I've mentioned before, the classical, if you allow that word, quantum computing is about concentrating the amplitude, concentrating the wave function amplitude in a solution. And that's how the Grover and Shor algorithms operate. And if you notice, there is no much progress on the algorithmic side for many years, just because it's a serious limitation. So there's 2 different paradigms. One is measurement-based quantum computing, and yet another one is simulated annealing, like D-Wave. Find me somewhere in the hall afterwards if you want to talk about that more. All of those are faced with the square root of n limit. Can we do any better? If you go to the assumptions leading to the proof that the square root of n is optimal, you will see that not necessarily the physics has to follow them. And that's where the startup-y part becomes important again. So, as I told you, classical backtracking algorithms are excluded just because you can't do the copy of the state. But if you think from the basics, you have 2 operations of your quantum processor at your disposal. One is almost arbitrary unitary evolution operator. And you know, any physicists in the audience, excuse my oversimplification. I'll not talk about the operators anymore. I'll just show you the matrices which in some representation actually represent those operators. So if you could have the backtracking, you could enhance the solution in the simple way. Measure, if you failed in your measurement, backtrack, measure again, and then the probability of the success changes into something which is growing like exponent, right? If you do this on the simple way, you are getting something which is also linear, only by a factor of 4 better than the classical linear algorithm, significantly worse than the quantum limit. How do you do this? Those 2 operations, Hermitian measurement, projection measurement, represented by the matrix multiplication in the top row. You get something like you want to measure the outcome A, which is regretfully, that's where the probabilistic nature of the quantum computing comes forward. Meaning you are just getting one of those results with certain probabilities, depending on the values of eigenvalues of this matrix, right? So assume you wanted to get the 1 in the state corresponding to 1 in the green marked box. Obviously, the first measurement failed, right? You got 0 there. But think about the unitary transformation. It just happens that it is the same operator Shor used in his algorithm, applied to the resulting state. Look at what happened. It is not the state we started from, meaning no cloning principle still holds, but essentially you got all the states represented again. And based on that, you can build, in the unstructured case, which is kind of sanity check, you replicate Groover's result, getting optimal measurement without extremely precise rotations he needs to apply. It's just this, very simple thing. Measure, rotate, just unitary matrix is the generalized rotation. And measure again until you succeed. So there is a new paradigm. Actually, this is patent pending. The patent is happening as we speak. And if this holds, then there will be a startup trying to implement that kind of hardware and that kind of algorithm operating from here in Poland. In summary, yes, the progress in quantum computing is happening regardless. We will get there just because of the miniaturization. There is a need of breakthrough in hardware, and as I've shown you on the previous slide, you can challenge some of the assumptions, still staying within the realms of physics, and get something which was not available to the classical quantum algorithms. And this is still a matter of the question is still open whether it can be used to attack NP-hard problems. Yeah, relative to the random oracle, it's impossible, proven. However, there is a structure, not so much in the NP-hard problem itself, but in the query structure. Verifying the solution of the NP-hard problem, by definition, has to be done in polynomial time. That belongs to the definition of the NP-hard, right? So if you can follow with your algorithm the structure of the query rather than the structure of the problem, then there is a chance of solving NP-hard problems in polynomial time. That was it. Thank you very much for listening.
Thank you.